The second part of Chapter 6 is all about graphing. We're going to focus specifically on sine and cosine functions, although there are graphs for the other four trig definitions. In this lesson, we're going to look specifically at how sine and cosine are formed, and then as we progress through the chapter, we'll look at transformations. To understand how sine and cosine are formed, we're going to use what we know about the unit circle, but we're not going to use it exactly the way you might think. If you have an equation like y equals sine x, the x and the y values aren't going to necessarily represent the coordinates on the unit circle. So here's what I mean. For y equals sine x, x stands for your input, and the input is going to be your theta value. Our graphs aren't going to look like circles, they're going to be curves on a coordinate system. Now the angle can be measured in degrees or radians. More commonly than not, we're going to use radian measures to define the input value. For sine, the y coordinate is going to represent sine at that theta value. And that's where the values from the unit circle come in. Remember, on the coordinate system, sine represented the y-coordinate on the unit circle, and we'll see how that transfers to our graphs down below. Now for cosine, it's very similar in setup. For the y equals cosine x equation, x still represents your theta value. And it's still going to be degrees or radians, so this is the exact same. And again, more commonly than not, we'll use radians. But now your output doesn't represent sine, it's going to represent cosine, or the x values at any given theta measure. When we describe domain and range for these nonlinear functions, the domain can be all real numbers. It can be any theta measure, negative or positive. We'll use theta values that we recognize from the circle, but really you could have any number you want. The range values now are kind of specific to the unit circle. Remember, on the circle, sine represented the y-coordinate. And at the very bottom, if we kind of pan over to that circle, notice at the very bottom, the smallest y value we have is at -1. And you go all the way to the top, the biggest y value is +1. When we think about cosine, the smallest cosine value was -1 on the left, and the biggest cosine value is +1 on the right. What that means for our parent functions for both sine and cosine, the range is going to be any values from -1 to +1. That's for just the basic function. After we apply transformations, the range can be changed. Taking a look at the basic sine function down below, you can see both sine and cosine. The dots that are marked on that curve represent the values from the specific locations on the unit circle. So here's what I mean by that. For sine, we start right here at 0, 0. And then that first dot represents the output at pi/6, or 30 degrees. The second dot represents 45 degrees, or pi/4. The third dot represents pi/3, or 60 degrees. And then notice at the very top of that curve, we're at pi/2. So the input values are coming from the inputs on the unit circle. But now notice it doesn't form an actual circle. So the input values, as they increase, move along the x-axis. Notice we have 2 pi on our graph. We also have 1 pi and 3 pi/2. Those are the unique quadrant boundaries for sine. Notice the top part goes up and then comes back down, so all your output values are positive. And then after pi, the values drop below the graph because y is negative between pi and 2 pi on the unit circle. We'll look more specifically at how the graph is formed down below. Over on the right, check out the parent function for cosine, and you'll see that it looks pretty similar to sine except for a couple of key features. Right out of the gate, we don't start at 0, 0 this time. We start at the top of the graph. And that means at 0, the cosine value is positive 1. And if you look at the unit pair, or the unit circle, the ordered pair is 1. As x increases to the right, your cosine values drop down to 0. And then as x goes to pi, your cosine values drop down to negative 1. And then it goes back to 0, and then back all the way to 1 when you get one full revolution around the unit circle. So notice over on the left-hand side where it says range is between negative 1 and positive 1. That matches with what we talked about from the unit circle. Down at the bottom it says period is 2 pi. You'll notice in bold that's kind of where we're getting those values from the unit circle, but the graph does continue on to the left and the right. The reason it does that is because the graph is periodic or cyclic. Cyclic means the graph will continue to repeat over and over on both sides of the y-axis, following the same pattern as what was found from the unit circle. Okay, here's where we're going to have some fun. We're going to take a look at generating the values for the graph in more detail. We'll start with the sine function. You'll notice I just have a very extended coordinate system, and this isn't going to have anything to do with a circle when we're done. What I want you to do is divide up the values on the x-axis with me. From the center, we're just going to keep that at 0. I'm going to write 0, or actually I'm going to leave 0. I'm going to count 3 to the right, and down at the bottom, I'm going to write pi over 2. That'll work not only for the values for sine, but it'll also work for cosine. I'm going to count 3 more over and put 1 pi. 3 more over again, 3 pi over 2, maybe, there we go. And then 3 more again, 2 pi. We're going to extend that all the way to the edge. So after 2 pi, when we count 3 pi, or 3, well, it's really far to go, there we go. When we count 3 more over again, we'll be at 5 pi over 2. And that's going to have the same output as 1 pi over 2. We're starting to find some coterminal measures. Count 3 more over again, and we'll go to 3 pi. 3 more, 7 pi over 2. And 3 more, 4 pi. There are 2 revolutions around the unit circle. After 4 pi, count 3 more. We'll be at 9 pi over 2. Count 3 more over, we'll be at 5 pi. And the graph can keep going after that. Now when we count in the opposite direction on the x-axis, we're just going to repeat those values backwards. Going 3 to the left, we'll be at negative pi over 2. 3 more to the left, negative 1 pi. Again, 3 more to the left, negative 3 pi over 2. 3 more to the left, negative 2 pi. And the values could continue on the negative axis, or negative side of the y-axis as well. For the y values, I'm going to actually double the dimensions on top and bottom for the y-axis. I'm going to put positive 1 up at like kind of the second square, and negative 1 down here. Oh, you can't really see that negative very well. Let's make sure we can see that visual. We'll do negative 1 down here at the square at the second square. Oh, I don't like that at all, you guys. Let's fix that. There we go. That's better. All right, thinking about the unit circle up above, let's go ahead and start plotting some of these values. At 0, the y-coordinate on the ordered pair was 0. What that means is sine of 0 starts right at the center of the graph. And while there are values that increase, I'm going to go right to the top of the circle when x is pi over 2. At pi over 2, the y-coordinate is 1. I'm going to go all the way over to pi on the left-hand side. On that left-hand side, the ordered pair is negative 1, 0, and that means your output for sine stays 0. Down at the bottom of the circle, 3 pi over 2, if that's the input, the y value drops down to negative 1. Remember, we're going 2 dashes for that. And then back to 2 pi, it goes back up to 0. So wait a minute, I'm off on that one. That looked weird. All right. There we go, that looks better. So notice those dots really are the boundaries of the coordinate system, or of the unit circle, using those coordinate system values from the circle. From here, what we can do is continue that pattern because the function is cyclic. We know that we stopped at 0, but if we go to the next kind of boundary, we'd go back up to positive 1. Go to the next boundary, 3 pi, we'd be back at 0. 3 more over to the right, at 7 pi over 2, we'd be back down to negative 1. And then at 4 pi, back to 0. So there's that second revolution around the unit circle, and continuing the pattern to the edge of our graph, it looks something like this. And we'll connect those dots to form that sine curve. But first, let's go to the other side to make sure we can get the dots to form there as well. If we want to continue the pattern, we want to have the flow of this curve be the same. What I mean by that is when we go to negative pi over 2, we'll actually be down at negative 1. At negative pi, we go back to 0. 3 pi over 2, positive 1. 2 pi back to 0. And those are all the dots that we're going to plot to sketch our sine function. As we start to connect these dots and form that curved pattern that we see up above, let's go right back to the center of our graph, right at 0, 0. I'm going to pan this over just a little bit to the left. As we start connecting these, remember this is a non-linear function. Notice the curve on the unit circle in quadrant 1 increases as the x values or as the theta values get bigger. The graph curves up towards to the top, and then it's going to come back down. From pi to 3 pi over 2, the graph is going to curve down low and come back up and continue on that pattern. You want to just kind of keep continuing, connect those dots. If you want to connect all the dots themselves, go ahead. I just kind of like the way to draw these curves in without having to make sure I touch all those dots, but it's up to you. And the graph will continue over to the right, so I'll put an arrow like so. If we go to the other side of our coordinate system and continue that pattern as well, it'll do the same thing. We're going to curve down low to negative 1, go back up to 0, over to the top, back around, and then over to the left. Now if we put this all together and kind of zoom back in, you can see the curve for the sine function. And what we'll do with that is make transformations that stretch and compress the graph and even move it left and right and up and down. All right, let's go ahead and try cosine. It'll look very similar to our sine function. Pause the video and draw in all of your input values from negative 2 pi on the left all the way over to 5 pi on the right. Then press play and we'll finish the sketch for cosine. Now that you have the x values marked, let's go ahead and start at the center and check out the pattern for cosine. Cosine at 0 is technically the x-coordinate from the unit circle. In this case, it's going to be positive 1. I guess I forgot to add those in there. So we have 1 at the top, negative 1 down there. Okay. If we let cosine start at positive 1, at the top of the unit circle, pi over 2, cosine equaled 0. Over at the left-hand side at pi, cosine equals negative 1. 3 pi over 2, it goes back to 0. And at 2 pi, one revolution around, cosine goes back to positive 1. Let's go ahead and continue that pattern all the way to the edge of the graph. At 5 pi over 2, we're back at 0. 3 pi down to negative 1. 7 pi over 2 back to 0. It's kind of calming just to connect these dots. 4 pi will go back up to 1, 9 pi over 2 back to 0, and then as far as we can get to the right at 5 pi, we'll be down at negative 1. Over on the other side, let's finish this up. Continuing our pattern at negative pi over 2, we'll be back at 0. Pi will be down at, or negative pi will be down at negative 1. Negative 3 pi over 2 back at 0, and then one revolution going negative on the x-axis puts us back up at positive 1. Now notice that cosine is going to look very similar to sine. We just kind of have it shifted slightly over to the right or left based on how you're kind of looking at the picture. Let's go ahead and start at the beginning. Get those curves to draw in. Cosine's a little bit more challenging to not make this look like V's going back and forth. We want this to be a non-linear shape. Draw that curve to show how those values for x change as you get closer to each of the boundaries. Like so, and we'll keep going to the right. Well, that one got a little away from me, didn't it? We'll fix that. Okay, get that to curve a little bit nice. Well, all right, we're just gonna go with it. Okay, arrow to the right, and then do the same thing, everyone, on the other side. And we're almost done. So thanks for sticking with me on this one. Curve this down, bring it down like so, back up and back, and then arrow to the left. And those are the two parent functions for sine and cosine. We'll look at creating transformations for both of these functions for the rest of Chapter 6.